Hello everyone, welcome to the course on architectural design of ICs. So, in the last few classes we have seen the basics which are related to this course, that means the basic like critical path, false path, what is false path, what is multi-cycle path, all these things. Apart from that, what are the VLSI design styles are available and how you can choose, that means, and what is the that VLSI design flow we have seen, that is FPGA flow or ASIC design flow we have seen. That were just to start or to familiar with why I need to know about this architectural design of ICs. So, this few classes was on that, to know about that, okay, these are the phases are there in VLSI design flow. So, from today we will start this algorithm to efficient architecture mapping. Okay. So, here what we will learn, we will see that several circuit I need to implement or I need to design. So, at the time how efficiently I can design those circuit, because these are the basic operation or these are the basic circuit which is implement anywhere to build up or to design one small, that means one big function. Okay. That means to express any function I need arithmetic operation, right. So, here we will see or we will focus on to design efficient architecture at the that means this component level, or these basic components will be designed in such a way, so that whenever I will design the bigger circuit, so at that time I can get the benefit of it. Okay. So, the first is that I suppose I need to design one 4-bit incrementer. Okay. So, 4-bit incrementer design means increment by 1. Let us consider first increment by 1. That means, I need a circuit which will give, if I give any number. So, at that time it will in each, and that means whenever I will put the numbers. So, at that time it will give me just plus 1. Okay. So, if I consider, suppose if I consider 4-bit, so that means I can give the values of 0 to 15. Okay. And I can get the value from 1 to 15. Okay. So, as to implement, whenever I will put 15, so at that time I need 15 plus 1, that is equals to 16. So, 4-bit, within 4-bit, that will not be covered. So, I at that time it will be 0, it will be considered as 0. Okay. So, how efficiently or what will be the architecture for one 4-bit incrementer design. So, that we will start with this algorithm to architecture mapping. Okay. So, to start with that, so what I need to design one 4-bit incrementer. So, 4-bit incrementer, suppose at that time if I consider this is my 4-bit incrementer. So, here these are the inputs, suppose this is A3, this is A2, this is A1, this is A0. So, at the output I will get this is S3, this is S2, this is S1, this is S0. So, I need to design this particular 4-bit incrementer in such a way, so that whenever I will give any of this 4-bit input, so I will get increment by 1 in each cycle, right. So, at that time what I have to do? I have to do, the thing is that how to, that means where from I need to start. Okay. So, that means first you draw in any that means whenever we design any circuit. So, at that time, at the very first, what we know about the gates also, what we know? We know the truth table, right. So, here also as this is one circuit, so if I draw how it basically truth table means what? What is the operating principle of that particular circuit, right? So, here I need to design one 4-bit incrementer. So, first I need to know what is that means operating principle of this 4-bit incrementer. So, that means now if I consider this 4-bit here A1, these are the 4 input bits. So, as this is 4-bit, so that means total 16 combination I will get. So, if I start with this 0 0 0 and at this particular side I will be mentioned this output. What will be for corresponding input bit, what will be its output condition. Okay. For 0 0 0 0, if I give 0 0 0 0, so at that time output will be this 0 0 0 1. Then for 0 0 0 1, it will be 0 0 1 0. For 0 0 1 0, it will be 3. For 3, it will be 4. For 4, it will be 5. So, just increment by 1, right. So, in this fashion I have to fill this total table. Okay. So, then 1 1 0, then this will be 7, then for 8 it will be for this it will be 7, it will be 8, for 8 it will be 9, something like this. That means, up to here I will get all 1, at the time it will be all zeros, correct. So, I have drawn the the corresponding truth table for this particular 4-bit incrementer circuit. Now, how it will work, that means this 4-bit incrementer, how it will work. So, from this truth table, that means for the input changes, how the output changes, that is the behavior of this particular circuit. So, now I have to make the connection for this particular output, what is the combination or logical expression with this particular input, that I have to find out. So, how we can find out that thing? We can find out that thing using Carnot map. Okay. So, I think this is very basics we have learned in digital electronic circuit design. Okay. So, for this particular bit, how this A3, A2, A1 and A0 is basically varying, so that I have to see. So, for that means for now for S0, if I want to describe the logical expression for S0, so at that time what I have to do? I have to put the Carnot map, right. Okay. So, here at this is A3, A2, this is A1, A0. So, this is 0 0 0 1 1 1 1 0 0 0 0 1. So, for 0 0, this is 1. Okay. For 0 0 0 1, this is 0. For this is 1, this is 0. Again for 0 1 0 0, for 0 1 0 0, it is 1. For this is 0, for this is 0, for this is 1. Okay. Then 1, for then this one 0 0 1 0 0 1. Okay. So, why? For 15 you see, for 15 this is 0, for 14 this will be 1. So, after that if I just, that means from the truth table, if I just make the, that means logical expression. So, at that time this S0 value will be if I make this as common, so at that time it will be what? It will be nothing but A0 bar. Okay. So, that means now I can write the expression, I have got the expression for S0, that is equals to A0 bar. Okay. So, then next if I just want to erase this, or if I start with a new page. So, for now what I have to do, again I have to find out the next expression, that means what will be the expression for S1. Okay. So, for S1, then again if I draw the truth table, sorry, for the, that means the Carnot map. So, at that time at this side this is A3 A2, this is A1 A0, this is 0 0 0 1 1 1 1 0 0 0 0 1 1 1 1 0. Okay. So, if I just go back to the previous slide. So, for S1 if you see, for 0 and for 3, okay, that is 0 and 0. For 1 and 2, that is 1 and 1. Okay. So, for 0 this is 0, for this is 1, this is 1, for 2 this is 1, for this also 0. Okay. Then again if I just go back, then if you see for For 4, what is the value? 0 here. Okay. And for 5, this is 1, for 6, this is 1, and for 7, this is 0. So, again you go back. Okay. For 4, this is 0, for 5, this is 1, for 6, this is 1, for 7, this is 0. Okay. So, in this fashion, if I just go at that time, what will happen? If you just, that means look at this. So, at that time what will happen? That means now if you just go back and then again if I just, that means it will be filled like something like this. So, if I just make this pair, sorry, this will be 1, sorry. So, if I just make this pair, at that time S1 expression can be written as A1 bar A0 plus A1 A0 bar. So, this is nothing but A1 XOR with A0. So, now that means the corresponding expression for S1, that is A1 XOR A0. So, this is the, that means truth table. From the truth table I draw this Carnot map, and from this Carnot map now I got the expression for S1. Okay. So, now again what I have to do? I have to find out the expression for S2 also. So, what will be the for S2? If I just draw again the Carnot map, A3 A2 A1 A0, this is 0 0 0 1 1 1 1 0 0 0 0 1 1 1 1 0. Okay. Now, if I just go back, so at that time if you see for 0 0 0 1 and 1 0, for these 3 this is 1, sorry, for these 3 this is 0, for 3 this S2 value is 1, for 4 this value is 1, for 5 this value is 1, for 6 this value is 1. Okay. Again for 7 this is 0, for 8 this is 0, for 9 this will be 0. So, that means up to 7, sorry, up to this 7 value, whatever I got, that will be again repeated, right. So, if I just then again if I just go to the next slide, for 0 0 0, this is 0, for this 0, for this 0, for only for this is 1. Okay. Then again you go back, then for 4, 5 and 6, for 4, 5 and 6 that is 1, for 7 again that is 0, for 4, 5 and 6 that is 1, for this 0. Okay. Then again for this will be okay. So, now if you just make the, that means pair of these 4, okay, and then again this one and this one. Okay. So, now what I can write for this particular pair, S2 value will be, what will be the S2 value? Here this A2 and A1 bar. Okay. For this particular case, plus it will be A1 A0 plus this will be sorry, not this will be A1 A0. So, here this is A1 A0 and for this that is A2 bar. Okay. And for these two particular case, it will be A2 and then A1 A0 bar. Okay. So, now what I can write, that is A2 A1 bar plus, if I just freshly if I just write the corresponding expression, A0 bar. Okay. Now, again if I just make these things common here, then what I can write, A2 A1 plus A1 into A2 bar plus A0 plus A2 into A0 bar. Okay. This is A2 A1 plus A1 into A2 XOR A0. Okay. But this is the corresponding expression for, if I just go back to the previous slide, this is the corresponding expression for this particular S2. Okay. Now, instead of that, what I can see from the previous slide, here if you see, if I just take one, that means you just, this is the, that means method which you follow, you have to follow whenever you are designing the particular circuit. Okay. Now, instead of doing that, there is another way of doing that. What is that? For that, what I have to do? Again I have to draw the whole table, that is A3, A2, A1, A0. Here this is S3, S2, S1 and S0. Okay. So, now 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 and 16. So, 0, 0, 0, 0, 0, 0, 0, 1. So, again I am just writing the corresponding truth table for this particular increment circuit. Why I am just coming later? first let me draw this once, then I am explaining. Okay, then this one is 1 1 1 0 and 1 1 1 1. Okay. So, for this is 0 0 0 1 0 0 1 0 0 0 0 sorry this is 1 1. For 3 it will be 4, for 4 it will be 5, for 5 it will be 6, for 6 it will be 7, for 7 it will be 8, for 8 it will be 9, for 9 it will be 10, then 11, 12, 13, 14, 15 and then 16. Okay. So, from this particular table visually can I that means draw any relation for this that means output changes with the input. Now, if you see, but first target to this S0. Okay. So, S0 if you follow, that means whenever this is 0, this is 1, this is 1, this is 0, this is 0, this is 1, this is 1, this is 0. That means, at that time by seeing this table, I can write that this S0 is A0 bar. Why I can write that? Basically what I am doing here, I am incrementing it by 1, right. So, if you just think about the adder that means architecture, at that time how it works, adder architecture, that means for sum it is A XOR B, and for carry that is A and B. If I that means choose this as 3 input, at that time it will be A XOR B XOR C, and this carry out will be AB plus BC plus CA. Okay. So, this is the that means corresponding logic for full adder circuit. Now, here what I am doing, I know that one of the particular value that is fixed. So, that means whenever I am just if I just draw one adder circuit. So, at that time if this is A and this is B, suppose this is A, this is B, and I need to produce the sum. So, here B is fixed to 0 0 0 1. So, that means this 1 will only affect this changes or whatever the input of A. The rest of the bit, as this is 0, so it will not affect. So, that means this 1 will be propagated to the MSB side. Whenever I have designed this particular adder, so at that time it will be if I just draw this particular circuit using this full adder. So, at that time what will happen? Okay. So, C in equals to 0, here this is A3, A2, A1, A0, but here what is happening? This is 0, this is 0, this is 0, this is 1. Okay. So, that means now for the sum, what will be the expression for this? For sum, this is the expression that A XOR B XOR C. So, here B is 0 and B is 1 and C is 0. So, that means if I just make 1 XOR with A, so at that time it will be just A0 bar for this S0. Okay. Then next, what is this? Here it can produce one carry, that is C1 if I write. So, at that time the corresponding and what will be the carry out here? What will be the carry out here? That will be A0, that means that is AB plus BC plus CA. Okay. So, C is 0 in both the case. So, only the AB. So, that means this is A0. B is 1, C0 is A0. So, here what will be the sum? That is A XOR here A1, this is A1 XOR with 0 XOR with A0. Okay. So, this is now if I just got the expression for S0, this is A1 XOR A0, right. Then again sorry, this is S1. So, now for C1 what will be the expression? If I just write AB plus BC plus CA again. So, here what is AB? A1 into 0 plus what is this? This is C0 into B means 0 dot plus what is this? C0 into A0, sorry A1. Okay. So, now this is 0, this is 0 and what is this? C0 is A0 bar and this is A1, correct. Sorry, not this one is, so C0 is A0. So, this is not bar, this is A0 into A1. So, now whenever I will try to find out this S3, so what will be the S3? S3 value is, now if I consider, so at that time it is A2 XOR with 0 plus this is C0. So, that means now A2 will be XOR with A1 A0. Okay. Now, what will be the C3 value? C3 value is again A2 into 0 plus A0 A1 into 0 plus A2 into C0, that means this A into C, that is A1 and A0. So, then C3 value is A2 A1 A0, correct. So, now if I want to find out this S4 value, so then this S4 value will be again this will be A3 XOR with 0 XOR with this is C3, this is C2, this is C1. Okay. So, then along with this means A2 A1 A0. So, if I write this will be A3 XOR A2 A1 A0. So, for 4 bit now I can got the expression for each of these corresponding sum values. Now, if I want to make it a generic case, if you follow the trend, that means this carry is basically propagating and it is XOR with the corresponding bit which is the input of that particular adder structure or this adder circuit, right. So, if I just instead of 4 bit, if I just want to make it a generic case, that means for n bit, what will be the expression for sum? So, if I just consider the, that means for n bit incrementer, what will be the expression? The sum expression will be, I can write that as a n XOR with a n minus 1, a n minus 2, a n minus 3 dot 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 up to a 0. So, now if you just write that for n bit, if you put any values, let us consider this is 4 bit. So, if this will be n minus 1. So, if we this is this S3 value, is, sorry, this is, okay, if this is S4, so at that time this will be A4, not this will be 1, S0, sorry, this will be 4, 3, 2, 1, as I am not considering 0 here. If I consider 0, so at that time this I can write. So, that means for 4 bit I am considering 0 to 3, right. So, that is why if I just make it n minus 1. So, at that time this will be this, that means if I consider n as 4. So, at that time it will be 4. So, that means the value for 4 bit will be 4 to 1. So, that is why this will be 1, this will be 4, 3, 2, 1, correct. So, for n bit this is it. So, this is n bit incrementer incremented by 1. In the next class we will see, okay, that in the next class we will see if I want to change this value, I want a circuit this increment by 2 or increment by 4 or increment by 8, then at that time from this particular circuit can I design or can I draw the conclusion that what will be the change, where will be the change, or how can I design the corresponding circuit for this particular this incrementer circuit, and we will see the circuit of this particular 4 bit incrementer in the next class. Thank you.